So, latency. We know it, or at least we believe it's a bad thing. Clearly, if given the choice of having latency versus not having it, we would not want it. But just because we have it, is that a bad thing? Is that going to prevent our applications or what we're trying to do from working? And as we look at like satellite-based systems, this idea of latency starts coming into the fold a little bit more. So I thought I'd talk a little bit about how that affects applications and what we're doing and kind of where we're at today. In order to do that, we need to consider how communication or how information is communicated over the internet. And to do that, I'm going to try to do this in the least technical way I can. Kind of keep this more for the layman than the technical. So there's this thing called standards called the Open Systems Interconnection Model, OSI. It's a 7-layer model that's been around for for quite some time. And the idea of it was, as networking became, this idea of where the two systems, in this case, maybe system A, system B, are not managed or run by the same entity, but we want to make sure that they can still communicate over this internet, if you will, which is kind of what we have today is the internet, but that's not how it started. And so they came up with this idea of this 7-layer model, and the idea was that sort of each layer on each side would communicate with the layer on the other side. So the physical sort of to the physical, and we'll look at this piece here. Let's get a... So the physical tends to be a little more local, and we'll look at that. But the network layer, layer 3, is the one that starts making it, this network information will make it to the network layer on this side, transport to transport, session to session. And that in this way, we might be able to independently write applications that can still communicate to one another. And so this was the idea behind this. The physical and the data link layers are really sort of locally significant. So, this is your Ethernet, this is your Wi-Fi, your satellite, your cable, your DSL, these types of things. These are all residential. I won't really get into commercial type services. And so those really only live here, and then they change. And so as this thing talks to something, it's something different, and then it's something different, and something different, and something different, and now finally it's on this side. So those are locally significant. We're not too concerned about that when we're thinking about latency, other than the type of service that we're looking at for that access. Like if it's satellite, can impose quite a bit of latency into the end-to-end communications. And so it does become important purely from sort of that latency standpoint right now. So the network layer, and the only one that's really in use today, certainly on the internet, right? Internet protocol. So this is IP. And that's where the term internet comes from. So that's really the only layer 3 protocol in use of any significance in a public infrastructure anyway. And then we have the transport layer, and there's a couple of flavors here that are really the only ones that have been around in any sort of form or fashion. That's UDP and TCP. And these are what's known as the transport layer. So the user datagram protocol and the transmission control protocol. And we'll talk about those two because that's what's in use today. The rest of this session presentation, there are some applications that kind of still use this. You might hear SMB and CIFS, server message block. And so this is sort of sharing drives like in a Microsoft environment. You may have heard about that. It still uses the idea of a session that becomes important, and latency then becomes even more important. I'll be talking about latency specifically in terms of how the transport layer gets affected by it. In most communications, that's where that matters. But for some protocols that do their own sort of session handling and acknowledgements, you can have some more issues there. And then there's presentation, which really isn't used much anymore. We usually think of these top 3, 5, 6, and 7 as just the application, HTTP or FTP or something along those lines. And that's not important exactly for what we're doing today. But I figured I'd just kind of throw it out there. You can skip ahead of if you want. But that was it for that. So let's go down here and take a look at a particular example, kind of generic as possible. So we've got 20 milliseconds that we can go, it takes to go from system A, and I do this as what we might see a traditional server representation, and then system B as maybe a traditional client representation. The idea of server and client is, in terms of communication, isn't generally that important in terms of how these perform or behave in terms of throughput, but generally speaking, when we think about this, because and it'll become more important as we look at why we're doing some things that we do today, and that has to do with security and firewalls, and then the idea of the client and the server becomes more important. So I will talk about that then. So if we've got a system, maybe this is Netflix, and we're streaming some information is what we want to do, and it takes 20 milliseconds to get from this system to this system. And then if we want to send some acknowledgement or something back, clearly we would go another 20 milliseconds. And so typically we would consider this a 40 millisecond round trip time. And so this is kind of how we think about latency, right? This idea. So we would think of it as 40 milliseconds. So when we use UDP, and that's what we've got here, System A takes all the data that it has to send, and it breaks it up into packets of information. The typical size that we're going to see, and there would be a little bit more here, and this would be related to the physical and the data link layers that would be sitting in here. And this whole thing, basically from here to here, needs to be about 1,500 bytes for Ethernet. Well, exactly 1,500. It's the largest it can be, not including the header, for Ethernet. And because Ethernet is so popular and in so many networks, that's kind of the standard. And so that's what we use today. So we see 1,500 as what you'll hear the term MTU, maximum transmission unit, and that's referring to all of this, the data that I want to send, and then this header for UDP and the header for IP that I need to put in, all has to fit in that 1,500 bytes. And so IP generally is variable depending on the options used, but we're looking at 20 bytes for that. UDP has 8 bytes, so there's 28 bytes here, and that leaves the rest, to be data. So we're going to take our information and we're going to break it up into these, 1,460-ish byte size chunks. Throw on this UDP information, this IP, which is a source and a destination sort of address that allows us to get this information from system A to system B, and then system B sort of reverses it, right? And then we can get back to system A. But that has to be in there. Now, with UDP, there's no, so you hear the term UDP, unreliable and reliable protocols, and UDP is considered unreliable because there's no mechanism within UDP to manage this idea that this data here actually made it to the system over here, and it made it in order in terms of, was it the third one, the fourth one, the fifth one, and did it arrive in that order? And UDP doesn't manage that for us. So we don't get any information about how well we're doing straight from UDP. But the flip side to that is we're free to send data, as we see here, as fast as we want. We can continually send and send and send and send nonstop as fast as we possibly can. We have no idea how it's doing, right? We don't know if it's making it, if we're sending too fast, if we should slow down. But if we're looking at trying to utilize whatever this access circuit is, DSL, cable, satellite, we can essentially easily utilize 100% of that access because we're free to send data as fast as we want. So that's a nice thing about UDP. There's no, in fact, this idea of latency doesn't really hurt us. This first packet takes 20 milliseconds from system A to system B. But once that's arrived, we've been sending nonstop. So this arrives immediately after, and then immediately after, and then immediately after, and then immediately. So 20 milliseconds doesn't really hurt us in UDP. We're free to send as fast as we want. That first packet took 20 milliseconds, or whatever the latency is, the one-way latency, and that doesn't really hurt us. It's not a big deal. So this is why this protocol is used in most streaming applications, whether it be VoIP, so voice over IP, or video over IP types of things. This would be the general sort of protocol that we would use to do that, because it's low overhead, because UDP, TCP, we'll get to that, has 20 bytes. And again, it's a variable, but that's the smallest we're generally ever going to see. A little less overhead, easier to implement, and we just stream along. And the other reason for that is if you're, say, listening to a phone, you're talking to someone, and we've broken up all that voice into these discrete packets of data, and something happens, and we lose, this packet maybe, or this packet, they just disappear. Things are happening pretty fast when you're sending voice over IP. These are coming, the spacing on these is about 20 milliseconds. So you're getting 50 per second. And if you lost one, look how long it takes to, I'm going to send 20 milliseconds, say, hey, I missed a packet, and then it's taking another 20 milliseconds, 40 milliseconds. By the time that's occurred, we've already been playing and listening to sort of, many packets along the way. So from a timing perspective, this really makes no sense. I mean, we hope these things don't get lost. We hope they don't disappear, but there's really nothing we can do about it. It's just going to take too long to try and, go back to this first system here and say, hey, I'm missing some stuff. Please, resend that to me. By that time, it's too late. And so for things that are streaming in nature, if things are lost, there's nothing we can do about it, really. So why try? And just hope that we have a good network in between. It's really all we can do. And so why not use UDP? We don't care about latency. We can send as fast as we want, and that would work, really well. And that's why they call it a streaming protocol. Now, there's another protocol that would often sit after UDP to help manage some of that. It's called real-time protocol, RTP. And it helps us deal with the streaming type applications, but they still use UDP as their underlying transport layer. So that's in a nutshell, using UDP. So latency doesn't hurt us. It works great if that's our application and that's what we're doing. And if we want to know, like I've ordered an internet service and it's a 100 meg service or 50 meg service or whatever it is, and I want to know, am I getting all my throughput or all my bandwidth? There's no better protocol for measuring that than UDP, because you can just send as fast as you want. The environment in terms of latency does not affect us or impact how well that does. That's not what's used over the internet, and we'll look at why that is. But if you're in a private network or an enterprise type network, then typically that's what you're going to see, because this is the one that makes the most sense and the easiest to implement. So that's UDP. We won't go too much more detail about that yet, unless something comes to mind. So TCP, Transmission Control Protocol, looks a little different and has a little bit more interaction going on. And so what we do here is, let's take a look here at TCP. So in this case, you hear the term reliable. So, it's a reliable protocol. And usually what they're referring to in that sense is the transport layer TCP. And it is reliable in that what we would do is System A, in this UDP model, System A is taking, there's some data over here that we're trying to send, and we sort of break it up into all these little pieces, and then we want to send that along, to this other system. In UDP, system A is taking this piece and sending it, taking this piece and sending it, taking this, so on and so on, and just sort of streaming it out, if you will. With TCP, system A would take this entire chunk of data and give it, if you will, to TCP to say, here you go. Get all of this from here over to there. And so that removes the burden of managing all the data from system A. You're essentially giving it to that protocol to manage it for you. And so TCP says, and then you're guaranteed that it's going to get over there if possible, if the network stays up, and you can still maintain communications. And so TCP is going to guarantee or make sure that happens. And if we lose a packet here, we lose a packet there, TCP will take care of it, and it will get it back to system B and make sure that all the data. So when system B gets all this data, it's going to look exactly like it did at system A. And so TCP is going to handle that for us. But to do that, it needs to have some mechanisms for managing that. And because we don't know what's going on this network in between, how well it is, how well it's performing, how much bandwidth there is, sure, it's system, in fact, at home, you're using Wi-Fi, you're using Ethernet. System A is connected at gigabit or 500 megabit or really high speeds. And then you get to your service provider and you're going over your DSL or you're going over your satellite, and it's already dropped down to maybe 100 meg or 50 meg. And then, what's going on everywhere in between, right? There's all kinds of, you have no idea. And so, TCP tried to figure out a way, well, how can we, manage around all that unknown that's going on in between? And so because of that, generally, TCP is not supposed to be, it's called slow start. It's not supposed to be just hammering out data like we did with UDP, where, hey, I'm just going to go wham, 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 just send this as fast as I can. No, we don't want to do that. We don't know that we can do that. We want to sort of test the waters first and see, can we? I mean, is this network in between us going to sustain this? And so it might send a couple packets. So those packets would get over here. System B would get it and say, send back an acknowledgement saying, okay, I got this. And now system A says, let me try 4 packets, and let me try 8 packets, and let me try 16, right? And it would sort of ramp up, and they call that a slow start. But you can see, if it's taking 20 packets, 40 milliseconds to go there and back, and, if you've got like 2 packets just going along, that's there's empty data wire here, empty wire there, and there's just a couple packets out here that are just moving along, finally get over here, then we get this acknowledgement, then you put out a few more packets, but there's just you're not transmitting the entire time. So if you are not transmitting, then you're not utilizing all of your bandwidth, right? And so in order to utilize 100% of your access, and that's typically when we think about internet speeds, we're really just thinking about how much our internet access speed is, because we know that most of what we're doing is to some system across that service, and that's going to be our local bottleneck anyway. And so we want to try to get at least that. And in order to utilize that 100%, we need to be transmitting nonstop. But TCP, by nature, doesn't really allow that, not initially. Now, Linux and Unix as operating systems have been historically good about, well, maybe not slow starting. They'll start really fast. They'll just start sending data. They've done a really good job at that. For better or worse, right or wrong, the reality of sort of networks today, it kind of makes more sense for that than networks of 30 years ago. And so that makes more sense. Operating systems like Windows have been very slow to sort of adopt that model. They have gotten much better through the years. They're not quite as fast starting up as Linux, but they're getting there. So once we get started, we're transmitting things as fast as we can. How fast is that? Is that the only limiting factor in that? We sort of have this slow start, and then I'll ramp up and I'll start sending nonstop, right? Well, kind of. So the other limiting factor to us sort of going nonstop or dealing with this unpredictability in the network, and the fact that System A and System B generally have no knowledge of each other. I mean, they're not run by the same companies, same people. I don't know how big B is, or B doesn't know how big A is, type of thing. And so we can't assume that they can handle everything we can send them. That's not a safe assumption. And so because of that, the system that's receiving the data, so in this case, I've kind of set it up so that System B, maybe is your browser on your PC, and you're reaching out over here to Netflix or Amazon Web Server or Amazon Prime Video or Hulu or whatever the streaming service might be, and you're trying to get something sent back to you in terms of a large amount of data. I mean, a 4K high def is probably on the order of 50 megabits, I imagine. Haven't looked at how the codecs are doing these days. But it's a lot of data to be sort of hammering down and need to maintain. And so that's a high bit rate, and can be a high bit rate. So what do we do? What the System B will do is, when we set up our connection to say, hey, let's communicate over TCP, and that's the other thing we hear is a connection-oriented versus a connection-less-oriented. UDP is connection-less oriented in that you just, this side here, System A, just send it. It doesn't know much about B. It just knows, and we want to say how it knows, to just send this data to System B. In TCP, it's connection oriented. System A can't just send TCP to B. B has to reach out to A to say, I would like to do this. A sends back and says, okay, let's do this. So they call that connection oriented. And when this sets up, they call that a three-way handshake in terms of how that happens. But it requires one system reaching out to the other. And that's also where we'll kind of come up with the client server sort of idea, in that the client's requesting services from the server. It's like going into the restaurant and you're the client, and then you're requesting services from the waitress, who's your server, right? And then they go, okay, yeah, we can give you this, and then the transaction happens. So it's very much similar in this, where the client's reaching out to the server to say, I would like something. Now, in that, during this communication, the client is going to say, this is how much data, it's called a receive window, that you may send me. So you may have so much amount of data, and that's in bytes, that you have not heard from me. No acknowledgement that I've received it, that things are okay, but you're still allowed to send it. And so there's a parameter, so there's a receive window for both sides, because a TCP session is full duplex, and that you can be sending simultaneously both directions. You don't typically do that, but you could. And so System B is going to say, well, you can send me so much, and if you haven't heard from me, then you have to stop until you hear from me saying, okay, I've received something, or I missed something. And so if that window isn't large enough to allow you to continually send based on how long it takes to get this, right, then you're not going to be utilizing 100% of your bandwidth. So if we take a look at an example here, so the receive window size, I tend to call this the pipe, or the data pipe. And if we were looking at an internet access surrogate of, say, 100 megabits per second, right? So that's what we got here. And we want to fill up on this TCP connection 100 megabits. We want to send that 100% utilization. So we want to transmit at 100 megabits per second. Well, then it's going to take 20 milliseconds for the first bit of data that we send to get over here. And then it's going to take another, and these are minimums, right, 20 milliseconds for that acknowledgement to come back. So that's 40 milliseconds that we need to be able to send for it where we have heard nothing, not a thing from this system here. But we want to be able to continually keep sending. And in order to do that, that's going to take 100 megabits. We need to do that for 40 milliseconds, right? So that milliseconds is 1,000th of a second. And so these are tens position, this is the hundreds position, and then this one is the thousandth positions. And so this is 1,000th, and so 40,000th is this, 0.04 seconds. So if we want to be able to do this rate, megabits per second, times this many seconds, that's a 4 million bits of data. When we talk about rates, like how fast something transmits at, speed, rate, we're talking about bits generally, so bits per second. When we're talking about an amount, like a size of something, like the size of my drive, I don't talk about it in bits, I talk about it in bytes. If I talk about the size of my receive window, I talk about it in bytes, not in bits. Because chunks of data as they're stored tend to be stored in bytes of things instead of bits of things as a smallest unit of sort of access. And memory's that way, and drives are that way, and many things are that way. And a byte, I'll clear this up here, is just 8 bits. And so if we just simply divide 4 million by 8, we end up with 500 kilobytes. That used to be pretty large. I mean, for a system to have that for one TCP session, I mean, you can imagine a server serving up 1,000, 2,000 clients, and each one of those, if they were receiving, right, that would be a lot of memory used up. To transmit, remember, this is a receive window. This is a receive window, not a transmit window. Transmit windows are typically bigger, but they also sort of have the same idea that this needs to be able to transmit without filling up that window, but they're generally larger. And so we need to have a receive window of this size, 500 kilobits. If system B, and because that was the pipe size, has a 500 kilobit, and this can change during this communication. So system B can start off saying I've got 600 kilobytes, and then it can go to I only have 100 because its resources are changing and what it can do is changing, and that can actually be updated during the life of the TCP connection. There are some parameters that can only be set up during the establishment. So if we have this, then system A is allowed to transmit pretty much nonstop because they're allowed to do 500. By the time they get to that 500th, to that last byte of those 500 kilobytes or 500,000 bytes, they've heard an acknowledgement back. Oh, and so that relieved some amount of data, and that gives them more data to send, and then they get the next acknowledgement, and then they get the next acknowledgement, and then the next acknowledgement, which keeps relieving this data, so now they can continually send. So as long as acknowledgements are coming back in a timely fashion, not getting lost, then in theory, this one TCP session could run nonstop at 100 megabits. So you can see as the latency goes up, this system needs to have a larger and larger value. Things like your personal computer these days have, probably megabyte, so millions of bytes for receive windows, because you have a lot of memory storage. Your computer, you're not typically doing thousands and thousands of connections, so it's not a big deal to have that. So that makes that work. Even portable devices like your phone, same thing. There's a lot of resource, and so generally speaking, we can accommodate 100, 200, 500 megabyte, even in this is a 40 millisecond delay. We could even go larger and larger. As this number is going up in terms of our latency, that's going to be impacting our performance for this single TCP session, right? And so the faster our speed that we're trying to achieve, and the longer the latency, the larger the receive window. So just because we have latency doesn't mean we can't deal with it. Doesn't mean we can't still, get a high throughput. We're always, hey, we're getting 200 megs, 300 megs, like even with Starlink, we're going to have 300 megabits. Well, and what does that mean? Is it achievable in every situation? And, what does it take in order to achieve that? And so as we look at latencies, right, and they go up, we compensate for them with receive buffers. Now, the other sort of nuance to latency is that's fine when we're just sort of transmitting and all we're trying to do is sort of stream or send information essentially from one side to the other. And with the high bandwidths, generally that's the case, right? You're streaming video. We're trying to do, a couple video streams. We need to use 100 megabits, but there's not a lot of back and forth that we need. It's just really trying to send, that's our goal. So latency in general doesn't necessarily hurt us in that case, other than the way TCP behaves, and we've been talking about that it's not really allowed to just continually send unless it hears back and has to, maintain or work within this receive window size. So there are caveats there, so it's not a guarantee, but in general, we can sort of work within that and make that happen. But if you have systems that are very interactive, and maybe I could see a gaming type thing where there's multiplayer online games and you're doing things and you're shooting and fighting, and the longer it takes for you to realize that somebody shot something, then the slower your reaction is going to be, and it's going to affect the behavior of that particular game and that environment. So there are some situations where this back and forth is needed, and the longer it takes, the more adverse the effect on what we're doing. So in those situations, there's nothing, latency is just bad, and there's nothing we can do about it. But is 40 milliseconds, is 50 milliseconds, is 100 milliseconds, what's bad in those cases, what can be tolerated? That's just going to vary based on the particular application and what's going on. But in the general case, for what most of us are doing, 20 milliseconds, 50 milliseconds, 100 milliseconds doesn't really hurt us. 100, and you're starting to get 100 megabits, right? If this is 40 and we triple this, right, we would need almost 2 megabytes worth of, and that's a pretty big receive window. You can configure your systems to do that by default. I suspect they don't. Maybe in another video we talk about how you look at that and how you measure those things. But in any case, it's probably not hurting us, right? And this is end-to-end, system A to system B, which is composed of many things at your house. I guess that would be sort of this way. Things at your house, and your access to the internet, and then sort of over the internet, and there's all this stuff that's going on along the way that's contributing to this overall latency. Because the latency that matters is the latency from system to system, and clearly, if you can remove some from any little piece or component along the way, that's just going to improve. And if you have internet access that is a fixed latency of adding 10 milliseconds, then you've got at least 10 milliseconds plus everything that's going on. So clearly we're trying to minimize or reduce the local latency as much as possible. And, you hear things like, we're going to get I think I've heard Starlink say we're going to get to 20, 25 milliseconds, something like that. Well, what does that mean, right? Are they talking in general from a system on this with a Starlink terminal, that's sitting here looking up at the sky, to the average server out there? Or are we talking just to get up to, this satellite up here in the sky, and so it's just get up and back, is going to be to the Earth, to the surface of the Earth, right? And so that's where the 20 milliseconds is. I suspect, in general, that's what they're talking about. is just to get from your terminal to a satellite and back to the Earth. And that would be without their satellite to satellite or inter-satellite communications, because then latency is a little different, because you're going to go up, you would go up from your terminal up to, a satellite up here that then goes to another one, to another one, to another one, and then back down. But this is where the server is, or near the server. And then you're going to come back. Well, what's the latency there? I guess, we had something over here, we had something over here to get up to the satellite system, down from the satellite system. So maybe if we think of this with this, and that's not sure, what they're talking about. In general, though, when we talk about internet access and latencies, we're talking about the latency to get from your terminal device or modem to the provider, the first piece of equipment of the provider, and then back, right? That would be the sort of internet access latency. And with the satellite system, you'd be going up and down, and 20 milliseconds with the low Earth orbit Starlink type system. In the other video we talked about that, certainly seems possible just from a physics standpoint. Additional latencies that they're probably getting are due to processing time on the satellites. And we'll look at how we measure latency and try to understand that in just a bit here. So it doesn't really hurt us, right? Latency, we can get around it. It's not the end all be all, destruction of communication. But, why are we using TCP instead of UDP, right? I mean, if the goal here for the large bandwidth or the high bandwidth systems is to continually send data, why are we using TCP instead of UDP? Well, that comes down to where this picture is here. Unfortunately, the internet is public, and we can't always trust everyone and everything that's going on. And so we tend to put firewalls to protect us from intruders or people that might want to do us harm. And the fundamental sort of basic way that the firewall is working is it is a wall, right, that's trying to prevent communications. And what it's preventing is anything out here trying to reach into the network and talk to a system. And so the default behavior for this firewall is it sees a piece of information, a packet that has an IP address that is taking it here. And then it's maybe TCP, it's maybe UDP, and there are others. We'll look at ICMP here. And trying to determine whether this is legitimate, whether this should be allowed. And so the way that the firewalls tend to do that is from a thing called a stateful inspection. And it's going to say that nothing is allowed in. So things this way, no, never. Unless this inside system reaches out, reaches over here to this system A to say, I want to do something, right? This is our TCP going on. It responds back saying, okay, let's do this. Now the firewall sees this initiation from this system on the inside, on the safe side, and says, okay, and it understands what this return should look like. There's certain, IP address, TCP information that says, okay, and it allows that. And so firewalls work on this idea that I see something, and so because I know that somebody here wants to do something, I will allow the return. And so it's stateful or dynamic in doing that. UDP has no state to it, right? Remember, it's connectionless, it's unreliable. And so this firewall has no understanding or way to know that some UDP packet coming in here should be allowed to go do something. And so that's the fundamental problem, with UDP. Now, there are protocols and ways of trying to say, well, maybe this system sort of talks to the server, and then once they've established kind of, okay, what's this UDP stream going to look like? Then, we would sort of tell the firewall, hey, this stream from this server and this thing is allowed. So now we can, and it's been in the works. It's experimented with. For whatever reason, it's not been taking off. And I think because fundamentally, TCP has been working because, really what does it take? It takes a large receive window, and the latency is not really hurting us. And we don't need the retransmission, generally speaking. But if we do have that much storage on this system, then maybe, and if we've watched, you watch Hulu, you've watched these different streaming services, and you will get, when you're watching this thing, then you'll get this little, and it'll say buffering, right? And what happened is that this video stream was this data stream that was coming in is interrupted. And so now it's waiting and it's collecting data and storing it here locally. And then when you start watching, you're pulling these data packets, if you will, off your buffer, not off the network. And you've already received them and you're just watching them out of the buffer. And hopefully, if there's some, and so we didn't talk about jitter. Latency is just, this sort of round trip time. But as this latency changes over time, so if at one instance it's 40 to go there and back, and another instance it's 60, and then another instance it's 30, as that changes over time, that's called jitter. And we don't really like jitter. It's not a good thing, harder to deal with actually. And so by buffering this, stuff is coming in and it's coming in at different rates that change, but that just means that our buffer is sort of, filling up and then emptying out and filling up and emptying out, filling up and emptying out. But if we run this buffer, we can sort of deal with jitter and just be pulling stuff off of here and hopefully, and maybe if we lose a packet, by the time our buffer gets up to that, maybe we've actually retransmitted and got it back in there, So depending on what's going on in this application, it may have the ability to do some buffering and manage that. And so certainly like on your TV, your smart TV, you'll see stuff like that. Your browser tends not to. I mean, the browser is built in. It's not an application made by Netflix or Amazon, whomever. And so you're kind of working within what the browser can do. So you're somewhat a little more limited there than you would be, say, on your phone and you're using a Netflix app to watch things. And the app is free to store and do things as it likes. And so, but you'll see those behaviors and you'll see buffering. But it's a way to sort of manage this by allowing it to sort of stack up. And it works, right? We've been somewhat, most of us don't have too many issues, and so TCP is working. So what's the big push, or why try to get UDP, and getting that sort of mechanism working where we can talk to the firewall to tell it that expect this UDP. But that's certainly possible and, is done in some cases. So the other thing, when we start looking at how we measure, you see these speed tests, right? You go out to whatever speed test website, and I'll probably do a video and show how that looks and break it down. But clearly, trying to measure the access on our is very, we want to use UDP, but how are we going to use UDP to measure the access, right? We can't even get our streaming to come through. So we can't use UDP to measure the performance in terms of the download anyway. Upload, yeah, sure, we could use UDP. That's fine. If the other server is set up to receive it and look at it, and that they manage their firewalls appropriately and they let that traffic in, sure. If you want to, in that open environment, they can more than happy to do UDP. They don't typically, but they could, mainly for the same reasons, right? They're worried about security too, and so they stay with TCP. So if we have TCP, how do we get or guarantee that we're going to get all this throughput when we can't guarantee that it's going to start up right away? We can't guarantee that the receive window that we're testing on is going to be big enough. So what these systems do says, well, that's a single TCP session, right? There's no requirement that says, oh, we can only do one TCP session. You can't send data over more than one. It's like, well, no, we can't. And so what will happen in these speed tests, and I suspect, although I haven't looked at it lately, is, if you're a streaming video service, you can be sending over several TCP sessions. There's trade-offs to that, and so you don't necessarily always want to do that. It's not always a good idea, and we'll look at that. And so we can request, many TCP sessions to run, and that, any one of them may not be able to fill up our, whatever our access is, 100 megabits. But if we run all of them together, then we should be able to completely fill up our circuit. And so what these speed tests will do is start running many sessions, and then they'll look at this data that's coming in from each session and try to figure out, how much is getting lost and what's making it through, and then figure, okay, I'm getting about this much as an aggregate through. So that's sort of the bandwidth. For any one of those, maybe it wasn't 100 meg, but if any one of them was 25 meg, then you put 4, 5, 6 of those together, then you're going to get 100% utilization. And so that's how those things tend to work. There are many TCP sessions. And that's fine from a speed test. You can start seeing how much you're getting through. The fact that 6, 7, 8 sessions is going to overload your access, and you're going to start, if this is your provider here, this is their equipment, and you're going to start dropping packets, right? They're just going to go away. That doesn't matter. You're just trying to see how much you can get through. You're not really concerned about, things getting dropped. That's great from testing and speed. But if you're trying to push video through and you decide I'm going to do 2 video streams, but that ends up sort of overloading, because it can be a little trickier to sort of manage that. But if you overload the access, then by basing too many streams, then you start dropping, and then it adversely affects the behavior or of the application. So, but if you control the send, you only do 25 on one and 20 on another, then I think you could do that, and I suspect some do. It's a little more complex from an application standpoint to manage it across 2 sessions, because now you're managing data from 2 different streams, and they're time oriented, so you need to make sure they're getting assembled correctly in time. So everything has a cost. Nothing's ever free when it comes to trying to get a sort of performance increase. It's usually a trade-off: complexity, time, storage, something. So let's take a look at how we measure this. What does it mean? How do I know I have 40 milliseconds? How do I know I have 10 milliseconds? And how do I know what my access is versus my end-to-end, right? From this system all the way over to here versus you to sort of your access provider. Well, the fundamental way for sort of measuring and determining latency is a protocol called ICMP, or ping. You hear the word ping, and this is Internet Control Message Protocol, ICMP, and there's a feature called an echo. I guess I'll look at it from this side. So an echo is an ICMP message type, and then an echo reply, right? And so what will happen is a system will generate, it needs an IP header to go to whatever system you're going to. Put in the ICMP header type, and then some data. Generally, these ICMP packets are going to be very small. The smallest amount of data for Ethernet is about 64 bytes. And so there'll be some data in here because we need to have it. Sometimes you'll put in a larger, I make this more like 1,400 bytes of data going through. And we'll look at that impact down here. It's a different sort of form or part of latency to think about. And so we're going to send this ping that's going to go out. It's going to be received by the receiving station, who is then going to send this echo back. And then what we do is we say, okay, at time 0, right, we send out our ICMP ping, and then at some time later, right, we receive this back, and we say that the delta between when we sent it and when we received it is our latency. from us to the system that we pinged. Now understand that latency or pings in general are sort of a low priority type thing. You can imagine that you're talking on the phone to someone, and then somebody walks up and is trying to get your attention, and you're looking at them like, you're kind of looking at them, and they're looking at you, but you're talking on the phone, and they say something, but you don't respond right away because you're busy doing something else, and then you respond to this person, and so there's a bit of a delay there, only because you were busy doing something else, right? So it's not a high priority thing maybe to deal with that person that walked up to you, or vice versa. And the same is true with ICMP. So there's always going to be a delay on this system that, yes, it receives it, but it may not readily just respond because it's got other things to do, and that's a low priority type thing. So the thing about pings is to understand that that's always sort of the upper bound, right? Because it certainly takes however long it takes. I mean, that was how long it took, but it's going to take some maybe longer time for this system to process it to then return the echo. Reply. And so this is an upper bound. That's sort of your worst case between you and some system. It's not a best case or a minimal case measurement. It's sort of the worst case. So if your worst case is looking pretty good, then you're doing pretty well. So that's but how do we know? We can easily sort of ping our system. That's an address we can kind of understand. Even because normally we would go into some abc.com, some site, and we can do a DNS lookup, and we'll talk about that. We can get an IP address for this, or we can just ping this name and let the ping utility itself determine the IP for us, and we can ping these sites and get a sense from me to this site, what's the latency. And so that's one form of sort of measurement, and that's our upper bound. Now, how do we know where our, shall we say, service provider is? So if this was our service provider equipment here, and we have some sort of access, media that we're going over here, and this could be DSL, this could be cable modem, this might be satellite, whatever the service is, and we're trying to get a sense of how much latency do I have just between me and sort of my provider, just on my access latency. Now, certainly all these terrestrial-based ones are going to have the best or the lowest case. So DSL, cable modem, even line-of-sight radios or cellular is going to be better because they're all terrestrial. They're pretty short, so they're going to have the best latencies. Fiber, same thing. I didn't put that in here, but fiber systems, they're all going to be pretty comparable. When you start talking satellite, where you're starting to travel thousands of miles, that impacts our latency for access. But how do we know what it is if we just want to get a sense of it? How do we even know what that first device is, right? So generally, and now this isn't always the case, you look at your default gateway, and we're not going to go into those things here. But there's an IP address, and that default gateway will generally, but not always, be the device in the carrier network versus something at your house. But sometimes, depending on what's going on, depending on the equipment you're leasing or getting and doing, it's possible that when you ping that, you're really pinging something at your house. And so you're not getting a real true representation of that sort of first carrier piece of equipment. For DSL, all right, so we won't get into because there are Wi-Fi router devices that carriers love to lease out, and that's what most of us who do this have, versus a pure cable modem or a DSL modem, the Wi-Fi router, in which case most of what you're measuring and thinking of is here. If you have a pure modem and you have your own router, then that gateway that you're getting, now you're starting to be looking out here versus looking locally, but we won't talk about that here. But another way to sort of look at all of the path in terms of all the pieces of equipment, basically routers that forward IP packets, is they do something called a trace route. And I'm not going to talk about that in any detail, other than a trace route is ICMP. It is not a protocol, kind of like echo and echo reply. It is an error. And so what happens is, you send a packet all the way destined for system A. And IP has this idea of a time to live. And if you set a time to live of 1, then the very first device that receives that packet will look at the time to live. It's going to decrement that time to live by 1. And if the value becomes 0, it sends an error back. So if the time to live was 5, then it's 4 here. And then, so now we started it with 5, we minus 1. So now it's 4, we minus 1. Sorry. Then it's 3, we minus 1. Now it's 2, we minus 1, and so on, right? And that's to keep packets from, in bad routed environments, from sort of just going around and around, because this router said to go here, this router said to go here, and they just sit here and loop and loop and loop, and that's a problem. And so to prevent those things, we have these thing called a time to live, and every router that forwards a packet decrements the time to live. And so if you set a time to live of 1, then the very first router that gets your packet will send an error back saying time to live exceeded. Now you know the IP address of that first router. You set a time to live of 2. Well, that's going to make it through the first one, and then the second one gets it, says, oh, there's an error, and it sends it back, and so on. So as you increment the time to live by 1, then you're going to start seeing, the next device, the next device, the next device, and you can trace out the path in your network. And once you have that, then you know the IPs, and you could then ping those. You could also look at how long it took to get the error. Again, errors are probably even lower priority than just a regular echo reply. So these are upper bound measurements of time as you start looking at that. But that would give you a sense of the different devices, and you could sort of maybe ping the first and or second one or third one and kind of like figure out what your access might typically be by reaching a little bit further into the network, but not too far, because you don't want to be looking at something in another provider's network. So that's ICMP. That's kind of how we measure latency to get an upper bound on what's going on. And so the other thing is, one other aspect to latency in terms of a contribution to it is this thing called serialization delay. And for services today, it's not as big of a deal. And so if we look at this packet, right? So here's a packet, and we've got our IP header, which was 20 bytes. Let's say this was TCP instead, and so there's another 20 bytes, so that's 40. We've got maybe 1,400 bytes, so we've got 1,500 bytes worth of stuff all together that we need to put physically onto whatever we're doing, onto the Wi-Fi, onto our cable service, onto our Ethernet, onto whatever that service is. And so if we want to do that, then we have to take all of those bytes, and what we're looking at here is 12,000 bits, right? Because this was 1,500, and generally, if you see a capital B, we're going to be thinking of a byte in terms of what that represents. And when you see a lowercase b, as we do down over here, we're talking about bits. So if this was a capital M, capital big B, then, or capital B, that would have been megabytes per second, and the lowercase generally megabits. It's just kind of a sort of a standard nomenclature. And so if we take the 1,500 bytes that we had, we multiply by 8 to get the number of bits, we're going to get 1,200 bits. So we have 1,200 bits of data that's in our memory or in our computer, and we're trying to get that onto the Ethernet, copper or the DSL or whatever it is. And so we're doing that at so many bits per second, right? And if we divide that by 100 megabits per second, well, it's going to take us roughly 1/10 of 1 millisecond to put that onto the wire, to serialize that data. And that's not too bad. I mean, we're talking about an end-to-end here of 40 milliseconds. And this is, clearly orders of magnitude less than that. It's sort of noise to what we're doing. And so with the speeds that we're generally looking at these days, 100 meg, 50 meg, the amount of time it takes to put this data onto the wire and to get it off the wire doesn't really contribute to our latency too bad anymore. But if your service is not 100 megs, if it was, say, only 1.5 megabits per second, and that's a standard DS1 rate, so that's a telecom, that's a sort of a commercial grade thing, but some DSLs were built that way early on. But what happens is, not only does our bit rate goes down, we're only get 1.5 megabits instead of 100 megabits, but the time to actually serialize this one 1500 byte packet is close to 8 milliseconds. It's like 7.8. And so now, nothing different. If we had our 20 millisecond end-to-end environment, but we switch from 100 meg to 1.5 meg, nothing else changes except now we're adding 8 milliseconds of serialization both onto and off of. And so our 40 milliseconds just went to 56 milliseconds round trip time. And that was only because it takes so long to take this data and put it onto the wire. And so not only are we only getting 1.5 megabit as our access rate, we're getting the benefit of a longer latency because of it. So serialization times can be a factor, but generally that's as the access rates go down, and they have to be pretty low to be of any significance, like below 10 megs anymore, which isn't really a big deal, or isn't that common. And so that's serialization delay. So hopefully that's been helpful, kind of give an insight as to latency's impact on what we're doing and how it affects us, and generally not too bad these days. And so if you're getting, even in satellite systems, if Starlink was to add, say, 25 milliseconds, right? And so they're adding that. So whatever you do, right, system, you're going to talk to some system and come back, and you know that because of your access, that it's essentially adding 12.5 in each direction, right? 12 this way and then 12 this way, giving you your combined 25 milliseconds. Then we're looking at, well, how much more, for the rest of this? And, generally speaking, from here to wherever you're going is probably going to be, less than 50 milliseconds, I would say. And so we're going to be, 50 plus 20, maybe 75, so maybe 70 milliseconds, which would just mean that we would need to up this to closer to a megabyte, which most computer systems are doing these days. So probably not impacting you too much. And so, but we do need to think about that. And when you do these speed tests, and I'll do one when I get my Starlink system, which who knows that'll be, remember that those systems are running these many, many, many sessions to say, this is the throughput I'm getting, which is great. And it's showing you the theoretical throughput that we can, that's sort of our access speed. And that's fantastic that it can get maybe 250, megabits per second. Then that's wonderful. But if the latency is still up there, then any single one is going to be potentially constrained. So as I watch my video over one of these, can I get 250, megabits? And what receive window, because it depends on the total latency, remember? And so am I going to be able to, to get that completely? And is that going to impact me? That just depends on where those are. And so as they build out their network, that's going to improve. And as they add the inter-satellite communications, they can make up some of that time. And if you look at my other video, you can see, theoretically, as they're built out, they can actually make up all of that time. And so that even though the access is 25 milliseconds, because they're actually able to run data faster in their network, they can essentially balance that out and you see no net loss. And so that will be interesting to see. Look forward to that. But that's what we have. So hopefully that was helpful. Thanks.